Okay, it's time to put some of these capacitor principles into a sample problem. So here's a system of two capacitors, C1 and C2. And notice the switch is open right now. And there's 120 volts across that capacitor from an external power supply. So that's with the switch open. And then we're going to close the switch. And when the switch is closed, we're going to figure out what the voltage is across here and what the charge is on C1 and on C2. The system electric potential energy as well. So let's do it. First of all, let's find the initial charge. The initial charge is C1V0. So keep in mind that this capacitor here isn't even in the circuit because we're putting the voltage across here. So we can like throw all this side away. So C1 times the voltage, which is 120 volts, and 8 microfarads. We got 8 times 10 to the negative 6 times 120, 960 microcoulombs. So that's the initial charge, and it's all contained in C1. The initial potential energy is, well, which formula of the three do we want to use? Let's use 1/2 CV squared. So 1/2 C is 4 micro, 10 to the negative 6, times 120 squared is 0.058 joules. So that is the initial electric potential energy. Now, that's also 1/2 Q0V, which is also 1/2 Q0 squared over C. So the other two forms for energy. It's time now to close the switch. Now keep your eye on it. There it goes. Is this a series or parallel circuit now? Well, keep in mind that the power supply was across these two. Well, it's across the one to begin with, and now we close the switch. So it's parallel because the 120 volts that was initially there from C1 had 120 volts across it. That's felt by both now. It's kind of like both of those components have the ability to share the charge unequally. They don't have to be the same. Okay, so hopefully that's clear enough. So what's this new voltage that we have? We haven't done anything else. We pulled the power supply off prior to closing the switch up here. C equivalent, because it's parallel, is the addition. And so the voltage is charge over capacitance. And the charge, we didn't add any charge by closing the switch. It was what was on C1 to begin with. It's now shared. So that entire Q0 over the new capacitance. So that is 960 microcoulombs over 12 microfarads. Micros go away. 960 over 12 is 80 volts. So the potential difference went from 120 volts to 80 volts. And of course, that voltage is the same across both. And now the new charges will be shared unequally.
Okay, well, I'd be happy to.
Okay, now let's go ahead and get the charges on the two capacitors. So Q1 is, by definition, C1V. Q2 is C2V. Charge is capacity times volts. So we got 640 microcoulombs. After all, what's C1 times 80 and C2 times 80? So we have 640 and 320 microcoulombs. Now they should add up to the original charge, and in fact they do, because charge is always conserved. All right. What's next? Well, let's find the new potential energy. 1/2 Q1V plus 1/2 Q2V. That's a nice form to look at it in. But you know that Q1 and Q2 together give us the original charge, so it's 1/2 Q0V, V being 80. So there it is, and that gives us 0.038 joules. But it was 0.058 joules. So where did the energy go? Well, in the process of the charges moving around, there's always some resistance. But even if there was no loss to heat as a result of resistance, perfect conductors say, we still have an electromagnetic pulse that is radiating energy away from the circuit. And now, with no particular smooth continuity, let me just time delay repetition, and let's do the capacitance of another scenario, which is an isolated sphere. So we have a sphere isolated in space. Can we express the capacitance of this like we can for two parallel plates? We're going to have to kind of think of this single sphere with respect to infinity is what it's going to come down to. C is Q over V, and the sphere has charge Q. Well, V is equal to 0 at infinity. That's what we want to think of it as. No surprise there. Then the voltage, and C is equal to Q over V. Let's solve for the voltage. Well, it's the potential at R with respect to infinity, and that's the integral of the E field across those limits. So that's KQ over R, as we've already thoroughly addressed. So C, which is Q over V, is Q over KQ over R. So it's Q independent, the Q's go away, and this gives us R over K. The radius over K, but K is 1 over 4 pi epsilon 0. That comes in the numerator, and we get 4 pi epsilon 0 R. Notice that the capacitance, ultimately, of an isolated sphere is not dependent on the charge or the voltage per se, but this is just based on proportional to the physical radius, which is perhaps a little mysterious. But nevertheless, that's the result we get there.